Okay, lesson 1.5, analyzing graphs of functions. Let's say, so we got a coordinate plane here. Let's say we had a point at -2, -3. And I'm going to fill that point in. And then our other point is at 5, 3, but that's going to be a circle. And now we're going to, we'll just sketch some kind of a graph that goes in between these points. So let's say, does that. Kind of an ugly looking graph, but anyway, we'll keep it at that. So this point here, so -2, -3, and 5, 3. And we want to identify the domain and range of this function. So the domain, as we know, is whatever x is allowed to be. And so it goes from a -2, and always start from the left going right, and on the range you start from the bottom and you go up. So -2, and since it's a filled in dot, it's less than or equal to x, and it goes to 5, but it doesn't quite make it because there's a circle there, so this is just a less than 5. Now this is a good way of writing the domain, but there's another way that I think is better, a little bit easier, and so the same thing can be written. A bracket, start off with a bracket, which means less than or equal to -2, comma, 5, and since you don't put another bracket, since it's not equal to, you just put a parenthesis. So these two mean the same thing. That's the same as that. I kind of like this way a little better. Seems like it's a little bit easier. Now let's see if we can identify what the range is. So the range from the bottom to the top, so we can put a -3, comma, 3. And then this is going to be a parentheses. So there's the range. Now, a lot of times you don't know what the range is if you haven't graphed it. For example, let's say we had the same beginning and end point, but let's say we had a graph that did this and goes up to that. Well, we don't know what the range is until we identify what the lower point is here. So if it's not graphed, there's a way of mathematically finding it, but it's a lot easier just looking at a graph. Okay, so let's do an example. Let's say f of x is equal to -x squared plus 3. And we want to graph this and find the domain and the range. Okay, so start off with a coordinate frame, and I think I mentioned this to you already, but use graph paper, obviously. Use straight edges when you can. Make your graphs look nice and pretty, and that way you'll be happy you did, and I'll be happy you did. Okay, so how do we graph this? Well, the first thing we'll do is just have a XY table. So X, Y. Okay, when X is 0, Y is 3. And when X is plus or minus 1, Y is 2. We could do another point, but I think this is enough. We know that it's a parabola. So 0, 3, we can go ahead and plot that. 0, 3, plus or minus 1, 2. So here, and now we can sketch it. Actually, when I say graph, I actually mean sketch. Sketch is a little less demanding than a graph. Graph is more, you want to be a lot more careful with a graph because sometimes you might have to get values off of reading a graph, but a sketch is just sort of what it looks like. And so we know it's a parabola. So something like that. Okay, now we want to find the domain and range. All right, so the domain, since it keeps going here and keeps going here, you know the domain is going to be all real numbers, or -infinity, infinity. Notice these are parentheses because you can't equal infinity. So whenever you have an infinity, it's going to be in parentheses, not a bracket. Well, let's look at the range. Remember, the range starts at the bottom and goes to the top. So the bottom value of the range is negative infinity. And the top, so we know that x is equal to, y is equal to 3 at that point. And since it's equal to it, we put it in a bracket. And there you go. Okay, our next example, we're going to find the zeros of a function. Zeros, also call them roots. So let's say we had a function. I'll just draw one real quickly. And let's say it's something like that. Well, we want to find the zeros of the function. So what we're actually finding is where the curve crosses the x-axis. So there's a 0 here, 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 and here. So this particular graph has, assuming that this keeps going down on the right and the left, we have 4 zeros. And we know that this is going to be an x to the 5th. No, sorry, x to the 4th equation, because we have 1, 2, 3 turning points. 3 turning points. The previous example, we did a parabola. It's a x squared, so we know it only has 1 turning point. So the number of turning points is 1 less than the exponent number. Okay, so let's do an example. Oh, also, the zeros are at where f of x equals 0. So here's an example. We want to find the zeros of f of x equals 2x squared plus 13x minus 24. All right, so the first thing we do is we set f of x equal to 0. So we have 0 equals 2x squared plus 13x minus 24. Well, the easiest way to solve this is, if it's factorable, go ahead and factor it. If you can't factor it, then you can always do the quadratic equation. If you have something like an x cubed or higher, a lot harder to factor, can't use the quadratic, and so pretty much you're stuck with, if it's a real ugly looking equation, you're stuck with putting it into a graphing calculator and letting it do the work for you. Now, remind me on our next Zoom meeting, probably should talk about graphing calculators. Some of you have them, some of you don't. You all might want to have them. It's going to be a requirement next year for calculus, so it may be a good idea to get one now and start playing around with it so you're an expert. Okay, back to the problem. So we can factor this. 0 equals, we'll put our parentheses here. Well, we know we have going to have a 2x and an x. And since this is a minus, right, a minus 24, we're going to have one has to be a minus, one has to be a plus. We don't know which. We can start out this way. Again, this is kind of a trial and error thing. So now we're looking factors of 24. Well, it could be 12 and 2, 24 and 1, 6 and 4, 8 and 3. Happens to be 3 and 8 work. Now, when you factor something, you always want to go back and multiply it out, FOIL it out, and make sure you get the original, because it's easy to make mistakes here. So now we separate these are both equal to 0, so we'll say 0 equals 2x minus 3. Solve for x equals 3/2. And we have the other one, 0 equals x plus 8. So x equals negative 8. When you get done, then sum it up and just say x is equal to 3/2, comma, -8. Put a box around the answer, and those are your zeros. It's the x values of the zeros, or where it crosses the x-axis. Okay, now we're going to look at increasing and decreasing functions. So let's say here's our coordinate plane, and let's say we have a function that goes like this, and we want to identify the increasing and decreasing parts of them. So this is easy to do when you're looking at it. So from here, this point here, to the peak right here, this is where the function is increasing. And then from here to here, it's decreasing. And then this is kind of tough, but say like from here to here, it's increasing again. And then at this point here, it's constant. So increasing, decreasing, or constant. So our last example, we're going to graph and describe the behavior. Graph and describe behavior of f of x is equal to x cubed minus 3x minus 1. Now, when I say describe behavior, this is what we're doing. We're describing if it's increasing or decreasing or constant. And also, we are indicating where a local maximum or a local minimum is, and we're also giving the intervals in which that occurs. So, if you have a graphing calculator, it's easy to plug this in and just see the graph. Also, you can go on Desmos if you have that app on your iPad, and you can graph it, or it'll show you the graph there as well. The thing is, and using Desmos is great. In a lot of ways, it's a lot easier than a graphing calculator. However, you can't use an iPad or a phone or anything else when you're taking an AP Calc test. You have to use graphing calculators. So again, if you have one, great. Learn how to use it. If not, go to Desmos or some other app and you can graph this. Okay, if you don't have that, you're going to start off with an XY table. So X, Y, and certainly we have to choose enough points so we get an idea what this thing looks like. We already know it's going to have up to 2 turning points because it's an x cubed function. Doesn't mean it has to have 2, but it can have up to 2 turning points. Okay, so 1x is 0, y is minus 1. 1x is 1, -3, 1x is -1, we have 1. X is 2, we have 1. -2, we have -3. This should be enough to give us an idea what it looks like. We'll first draw a coordinate system, and we'll just put in these points. I'll do it in red. We'll put in the points first, then we can sketch the graph. So 0, -1, 1, -3, -1, 1, 2, 1, -2, -3, -2, -3. Well, this is enough because we know it has up to 2 turning points, so we're going to assume it's 2 turning points, and so we can kind of sketch it from here. Now, we don't know at this point if it goes below this -3 point or not, but we can pretty much assume it's just going to go through here and then back up. Now, this is kind of an ugly looking graph because my maximum and minimum points look more like a V instead of a U. It ought to be rounded off. But anyway, now we want to describe the behavior. So we know it's increasing. And what's the interval it's increasing? And remember, we're starting from left to right. So it's increasing from -infinity to this point here, which is a -1. Now this is confusing part. Remember, you are only describing the x values, not the y values on this interval. So these are both the x values, okay? And next, it's decreasing on -1, x value of -1 to the x value of 1. So here's the area where it's increasing, and here's the area where it's decreasing, and then it goes increasing again from here. So we're going to put that, describe, so it's back to increasing from x equals 1 to infinity. Okay, what else do we want to do? Oh, we want to describe maximums and minimums. At this point here, at x equals -1, this is a local maximum because it's higher than its closest neighbors. So this is a local maximum point. This point here is a local minimum because it is lower than its close neighbors. We don't have an absolute max or an absolute minimum because we know this curve keeps going down to -infinity and it goes up to positive infinity, so there's no absolute. So we'll put local max at x equals 1. Don't just say local max equals 1. You have to say local max at x equals, whoops, it's x equals -1 though. Okay, and then the local min, if I can learn how to spell, I'll be a lot better. Local minimum at x equals 1. Okay, the rest of this section is more a lot of graphing calculator related, or when it's talking about related rates, it's more calculus related, and we can wait until calculus to get into related rates. So this is it for 1.5, and I'll post the homework on BrenWeb.